guys, today's lesson is on isotopes and average atomic mass. For today's lesson and pretty much all lessons going forward in chemistry, we're going to need our calculator and we're going to need our periodic table. So that you should have ready to go pretty much anytime you walk into class or anytime you work on your chemistry stuff on at-home days. So before we get into the notes handout today, I thought we could do a little bit of a review. So for our review today, it says an atom has an atomic number of 82, a mass number of 207, and a charge of positive 2. So we're going to ask ourselves first, what is this element? So the first thing I notice is I see this atomic number of 82. Atomic number is that number on the periodic table that is above the symbols. So if I go try to find 82 on my periodic table, oh my goodness, there he is right there. This is lead, you guys. We have found lead. So what element this is the element lead. Okay. Now it says, how many protons does this element have? Well, atomic number is the number of protons. So that number that is looking at your face on the periodic table is going to always represent not only the atomic number, but the number of protons as well. So this has 82 protons. And once again, if I change that number to not be different than 82, I'm no longer lead. The number of protons identifies what element you are. Okay, then I go mass number of 207. So that mass number of 207 tells me how many total things are in the nucleus of the atom. That gives me the sum of the protons and the neutrons. So to find neutrons from my mass number, I have to subtract from 207 the number of protons, which we said was an 82. And do not feel bad. I totally use my calculator for most things, even if it is simple adding and subtracting. And my calculator is telling me that we have 125 neutrons. So my protons were 82. My neutrons were 125. And I did this a little bit out of order, but that is okay. And the last thing I want to do is figure out how many electrons this atom has. If they did not say the atom had a charge, then we would know the electrons would equal the protons. Negative things have to equal the positive things. That would be 82. But here we have a charge. And the way I figure out how many electrons I have from the information of a charge is I say, okay, this positive 2 lets me know that there are 2 more positive things in the atom than there are the negative things. So that kind of helps me scale the number of protons to electrons. I have to have more positive things than negative things. Now I cannot change the number of positive things because that changes the whole entire element. So I have 82 protons, right? 82 protons. So if I want the number of electrons to represent that I have 2 more protons, then my number of electrons is going to be 80. So if I'm looking at this number, I have 2 more positive things than I have negative things. So let's see how good we did with this fun little review. Yay, looks good to me, so I'm real excited. Okay, so we're going to talk about isotopes now. So now we're on our notes handout. So isotopes. What is an isotope? Isotope was one of your definitions from your notes lesson last time. But as a review, it says atoms of the same element can have different numbers of neutrons. The different possible versions of each one of those elements are called isotopes. Okay, so we have 3 pictures here of hydrogen. We've got hydrogen with a dash with a 1. That means that hydrogen has a mass number of 1. And once again, mass number is protons plus neutrons. So we see we only have one thing in the nucleus and it happens to be a proton. So this version or this isotope of hydrogen has 1 proton and 0 neutrons. Moving over here, though, hydrogen 2, now I have, that 2 means I have 2 things in the nucleus. Still got to have only 1 proton or else I'm not hydrogen. But here I have added a second subatomic particle in the nucleus by adding 1 neutron. And then finally I have hydrogen 3 over here, you guys. And hydrogen 3 has 3 things in the nucleus, has to have 1 proton because he is hydrogen. That means he has got 2 neutrons. All elements will have different versions of themselves are isotopes in some form or another. Okay, so one thing I want us to keep in mind about these isotopes is that they all have the same number of protons. So all have same number of protons. That's super important to know. What they have different is the number of neutrons. And what I want you guys to look here, they write down the mass number down here at the bottom of all three of those. And you can see that mass number changes. So not only did the isotopes have different numbers of neutrons, you're going to see that represented usually as the mass number being different. So we're going to write mass number different. Cool. Okay, I love that. So for example, I didn't even read the thing. It says, for example, the most common isotope of hydrogen has 0 neutrons, and the two other isotopes of hydrogen are known as deuterium, which has 1 neutron, and tritium, which has 2 extra neutrons. So hopefully that tri means there are 3 things in the nucleus. Okay, here's another example. Here is 3 different isotopes of oxygen. We have oxygen 16. Once again, that number coming at the end represents mass number. Oxygen 17 and oxygen 18. All of the oxygens need to have 8 protons because last time I checked on my periodic table, I've got an atomic number of 8, right? So my oxygens, they differ in the number of neutrons. Here I have 8 neutrons for this oxygen 16 atom because 8 protons plus 8 neutrons is going to give me that 16 for that mass number. Now oxygen 17 needs to have 9 neutrons because 8 plus 9 gives you 17. And then finally, oxygen 18 will have 10 neutrons because the sum of the protons and neutrons equals 18. So once again, you are seeing this very, very intense difference in the number of neutrons. And as a result of that, their mass numbers being different as well. But the thing that is the same is that they are the same element. Amazing. Okay, so symbols for isotopes. We talked about this yesterday. Okay, there's 2 ways to write our isotope symbols. There is this number up here, you guys. We know that number is the mass number. You'll see me abbreviate that a lot as just MN because this is a lot of letters for me to write. Okay, and then mass number once again is the sum of protons plus neutrons. And then I have right here is I have my element symbol, which tells me what element I am. And then the last number on the bottom left is my atomic number, which once again is the number of protons, right? Another way to represent information about an atom is if I have the name of the atom followed by a dash and a number at the end. That number at the end is a mass number. And that's pretty much it. Let's see what we got next. Okay, we have a practice problem. I actually went to switch down to the document camera fully for a little bit for us to see if we can knock this out together. Okay, I'm going to zoom in. Well, maybe I won't zoom in. We'll see. We'll see what a zoom in looks like. Yeah, that's not so bad. Okay, cool. So it says naturally occurring carbon consists of 3 isotopes. We have carbon 12, carbon 13, and carbon 14. Once again, that number at the end is mass number, things in the nucleus, protons and neutrons. It says state the number of protons, neutrons, and electrons in each of these carbon atoms. So I've given you the isotope notations, and now I've turned it into these symbol notations. I can get the same information from both forms, but let's now, as a review, try to see if we can count the number of protons, neutrons, and electrons from all of these examples. Okay, so for this one, the number of protons for this isotope of carbon is always going to be the number in the bottom left, 6. And you guys, that number in the bottom left will always let you know that it is the same number as the number you should see above that letter on your periodic table. So once again, if that 6 was not there, I would still know it's supposed to be 6 down at the bottom because he's carbon. And carbon's atomic number is always 6. Anyways, that's the number of protons. To solve for neutrons, I like to think of this kind of being like a little setup for a subtraction problem. Like if you're in kindergarten or something. Well, maybe they don't do this in kindergarten, but elementary school where you would go 12 minus 6, right? And the sum of 12 or the difference of 12 minus 6 is 6. So that's how you get your neutrons. You just subtract those 2 numbers. And then I don't have a charge up here. So if there's no charge, that means the number of electrons is equal to the number of protons because protons are positive, electrons are negative. So also 6 there. Very cool. We're moving on to the next one. See if this one's going to be a little bit different. Protons, 6, because he is carbon. Neutrons is going to be 13 minus 6, which will be 7. And then once again, no charge up here. So the protons have to equal the number of electrons. So I also have 6 electrons. Amazing. Okay, last isotope of carbon is I have carbon 14 and still got 6 protons because he is carbon. 14 minus 6 will give you 8 neutrons on this guy. And then he is still neutral, so that means that the number of protons equals the number of electrons, so I'm still dealing with 6 electrons. So once again, you're seeing these different, sorry, you can't see, different number of neutrons, right? And you're also seeing these different mass numbers. Mass numbers. Cool? Amazing. Thought we would run through a few more just to kind of feel warm and cozy inside, because next time I see you guys, we're going to have a little quiz on counting protons, neutrons, and electrons, which is super exciting. Okay, so here's an example of an isotope notation. I have nitrogen 15. Ooh, number of protons. Where am I going to get that information from? I can look on my periodic table. Nitrogen. Where is nitrogen? Oh, there he is. He's atomic number 7, so that tells me I have 7 protons. Okay. Now I'm going to figure out the number of electrons. Remember, isotope notation, they cannot display a charge, so you have every reason to just assume that this is going to be a neutral atom, which means the number of electrons are also 7. Now, number of neutrons is where we do the little math. So once again, this is my mass number. Right? Mass number minus the protons will give me neutrons. So I'm going to take 15 minus 7, and that will give me 8. So I have 8 neutrons. Yes? That is cool. I love that for us. All right, next one. I'm going to do one more because I think this one is kind of fun. So this one right here is a symbol notation of chlorine, right? Or it looks like it is also a chlorine ion. Once again, an ion is the term that we use to describe an atom that is not neutral. So we're going to tackle that here in a second. But the first thing they're asking us to do is figure out how many protons I have. You were like, where's that number? No matter. The periodic table. Let's check him out. Find chlorine. There he is. Tells us we got 17 protons. So I can write 17 right there. If you want, if it makes you feel better, you can put that there, but it is kind of, like I said, redundant to have both of those pieces of information because they will always go together. Okay, electrons, let's tackle this. Now, sometimes you'll see if there's only a magnitude of a 1 charge, whether that's positive 1 or negative 1, we do not even write the number 1 if you would like to, and if it makes you feel better, that is super fine. Sometimes you'll also see when charges are written, sometimes the magnitude will come before or after the sign. So that's a way to represent charge. Either one of these things is totally okay. So just do not freak out if you see both versions here. Okay, so going back to this, it looks like I have one more negative thing in this atom than I have positive things. If I have 17 positive things, I can have 18 positive things to show that 1 extra negative than I have my positive. So 18 electrons. Okay. And then last but not least, we got neutrons. Once again, here's my little subtraction. 37 minus 17. Do not, if you need to get out your calculator, I like getting out my calculator for most of this stuff just to make sure I get right answers. But I'm pretty sure the answer to that is 20. Okay, great little review. Now let's get into the kind of the new material for today's lesson. So I'm gonna go back to our thing, and that was just what we did together, which is real cool. Oh, one thing to keep in mind though is if I wanted to turn this atom into an isotope, what numbers would I have to change from the numbers that we have represented on this screen? Well, to make an isotope, we're dealing with different numbers of neutrons. Also, that would change the mass number up at top. So that's our heart of the lesson today. Okay, so looking now, it says, how many isotopes can one element have? Can an atom just have any number of neutrons? Like, can I have carbon 45 or carbon 47 or carbon 2? Well, it depends. There are preferred combinations of neutrons and protons, though. And the reason for that is because as you get further down on the periodic table, stuff gets real big and real clunky, and you kind of want the stuff in the nucleus to kind of match each other in a somewhat equivalent ratio. That can be more easily displayed, honestly, up in the light elements. So it says lighter elements, meaning the ones up at the top with the smaller atomic numbers. They tend to have about as many neutrons as protons. You'll see that usually when you're working your problems with these smaller elements, that the number of protons are kind of close in some way to the number of neutrons. However, as I get further down, heavy elements, actually, since they're kind of wanting to be a little bit unstable to begin with, they need a little bit more neutrons than they have protons in order for them to stick together. So it's very common that down here on the bottom, you could have something with an atomic number of 85, meaning 85 protons, and it's going to have something like 130 neutrons. So that's typically what we see. But we got to kind of be somewhat within reason on the number of protons and the number of neutrons within an atom, because atoms with too many neutrons or not enough neutrons, they'll maybe exist for a short while, but they eventually come unstable. And what I mean when they become unstable is that they kind of decay or fall apart, which is kind of exciting, kind of scary. So do atoms just fall apart if they don't have the right number of neutrons? Yes. Unstable atoms are radioactive. Their nuclei change or decay by spitting out radiation in the form of particles or electromagnetic waves. So at the end of the school year in May, we're going to have a whole unit on nuclear chemistry, and we're going to talk about these really cool decay processes on what happens when atoms become unstable. So that's something super fun for us to look forward to. Okay, let's talk about this. This is not represented in our notes handout, but this is a good conversation that will lead us into our lesson on average atomic mass. How do your teachers calculate your grade in my class? So we have different grading categories, which are each worth different amounts, like your major grades, like your tests are 50% of your overall average, quizzes are 20%, labs are 20%, and homework is 10%. Now, your average in my class is a weighted average of all of these grading categories, right? So what that means is that if you're dealing with some of this situation right here, let's say you have a 100 in the homework category, you have an average of a 90 in the lab category, you have an average of a 70 in the quiz category, looking really good. Oh, we're a good student. But whoa, your major grades are a 30. Now that is going to be much more significant in terms of leading into calculating your average as pulling a little bit more weight. And in fact, if I were to calculate here, and we'll practice doing this when we do it in terms of the atom, wow, I am not passing my class. That is reason for concern. Even though I have a 100 in my homework, this 30, this major grade is really bringing things down. Okay, so this brings us into average atomic mass. Now, y'all have probably been freaking out because of this bottom number on our element blocks. You're like, why isn't she talking about that? She just keeps saying that's not the mass number. Well, it's not. It is the average atomic mass, and that number is listed on your periodic table. It gives the mass of an average atom of that element. It's a weighted average that's based on all of the possible isotopes of that element and also their percent abundance. That means carbon 12, I can have carbon 12, I can also have carbon 13, I can also have carbon 14, but whichever one of those isotopes is more abundant, meaning I see more of them than the others, that's going to carry a little bit more weight when I'm trying to calculate an average of the mass of an average of one of those elements. So average mass is not going to be a whole number because it is an average of all possible isotopes of our elements. Okay, steps for determining the average atomic mass. It says you're going to turn the percent into a decimal by dividing by 100. Then you're going to multiply that decimal by the mass of your isotope and do that for all the isotopes. Add the masses up, round to the hundredths. Okay, so we have an example. I'm going to switch back to the document camera so we can do this together. So you'll need your calculator. So it says magnesium has 3 possible isotopes. Calculate the average atomic mass of magnesium. So here I've given you the isotope magnesium 24, magnesium 25, magnesium 26, and also the masses of these isotopes. If you'll notice, it kind of matches, which is good news. Sometimes the mass is technically not exactly perfectly that number, which we'll go through an example here in a second, but it'll be pretty close. So here's my mass, and it's showing you the percent abundance of each one of these versions of the isotope. Looking at them, it looks like magnesium 24 is found a little bit more commonly, 78.7% of the time. If you grab a sample of magnesium, it's going to be that one, right? These other ones are pulling a little bit less frequently occurring weight. So we got to accommodate for that. I can't just say 24 plus 25 plus 26 and, oh, I'm going to divide by 3 because there are 3 of them. No. So here we go. So the first thing it said that I needed to do in my steps is to turn that percent into a decimal by dividing it by 100. To divide by 100, you are basically moving your decimal place 2 places to the left. So that represented as a decimal is going to be 0.7870. This one, moving my decimal 2 places that way, I got 0.1013. And then 2 places this way, that 11% turns into a 0.1117. Cool. So I've done that. Now the next thing I'm going to do is I'm going to multiply this decimal by the mass of that isotope, right? So I'll multiply the mass of the isotope by its percent abundance. And it looks like they're giving me a space to write down my answer. I've got my calculator. We are ready to go. It goes 24 times 0.7870. So I got 18.888. Don't worry about rounding yet. We'll take care of that at the end. And in fact, I'm going to show you the correct way to actually solve these problems, but this models exactly in essence what we're doing. So then I do it for the next isotope. I got 25 times 0.1, 25 times 0.1013, and I get 2.5325. And then my last isotope is 26 times 0.1117, and I get 26. Wait, no, I don't. What did I do here wrong? 26. Oh, I didn't even multiply. So here we go. Let's try again. 26 times 0.1117. Okay, there we go. I was like, that looks a little bit wrong to me. Okay, so now I got 2.9042. Okay, so I've done that. So those I'm going to add all up, and they're going to give me that weighted average. So if I round all of that up, I get straight from that 24.3247. And calculating the average atomic mass, we're not dealing with sig fig rules because those numbers, if I look at my periodic table, that average atomic mass number is going to be rounded to 2 decimal places. So we are also going to round it to that hundredths place, which means I'm going to stop right here. So my average atomic mass of magnesium is 24.32. And if you'll notice, the units for average atomic mass are AMU. So that kind of models out what it is that we're actually doing in a really cute chart formation. But the way that we're actually going to do this in class, and I think you'll enjoy this a lot better, it has you type way less things in your calculator. It has you not have quite as many opportunities for mistakes in your math. We're just going to, with our parentheses, represent this the product of the mass and the abundance each time and separating that by a plus for each isotope. So what that means is down here on the bottom, we're going to write 24.0 AMU because that's the mass of my first isotope. And we're going to say times 0.7870. And that's the percentage in decimal form for that first isotope. And then I can go plus, right? And then I can go 25.0 AMU. And we're going to multiply him by his percent abundance in decimal form. Plus, then I have 26.0 AMU times 0.1117. Yes? And then that can just equal. And that would be an appropriate way to show work. You've shown me that you are multiplying the mass by its percent abundance for every isotope, 1, 2, 3, and you are adding those up together. And I bet you if I type it in my calculator as one long stream, it's going to give me my answer, which we like a correct answer. Let's see if I can do a little bit better about typing my stuff in. And by the way, you guys, even though I wrote my things in parentheses just to kind of visually check mark yourself to make sure that you're doing the process correctly. Your calculator knows order of operations, which means if you just hit times and then number and then plus and then number and then times, your calculator is going to know to multiply those clusters of 3 first to add them. Okay, so when I do that, if I type that in my calculator, I go 24 times 0.7870 plus 25, let's see, times 0.1013 plus 26 times 0.1117. Okay, cool. There it is. Same number. So that's amazing. We're like, that's my average atomic mass. Average atomic mass is represented or rounded to the hundredths place on my periodic table. So that's how I'm going to show it here. And by the way, this should show the average atomic mass of magnesium. So like you kind of have a way to check your answers by finding these elements on your periodic table. And yeah, there it is. And granted, in creating these problems, there will be some slight discrepancies. So do not get real freaked out if you're like, oh, how was I off by 100th? That is not feeling good. There's potential for us to be off a little bit just because of the person who has made these problems, myself, is not great at really tagging in to try to get it exactly to match your number on your periodic table. But it is always great to check, because if you're getting something like 582 AMUs, that is nowhere near close what you should be getting here. And that is a great way for you to be red flagged to go back and like check your work. Yes? Okay. So what I actually want us to do is I want us to do some practice maybe. So I've given you guys some practice assignments and I thought we could kind of chew through some of those. I think I mostly, let's see what I want to do. I think what I'm going to do is I think we are going to do number... Yeah, okay, I think we're going to do number 3. Let's do number 3. Hop on down to number 3. It says lithium has 2 naturally occurring isotopes, lithium-6 and lithium-7. If the average atomic mass of lithium is 6.941 AMU, which isotope is the most abundant? Okay. So once again, this average atomic mass is a weighted average, okay? It's not going to be exactly in between these 2 isotopes. It is not a 6.5 because one of these is more abundant than the other. Based on that mass I see right there, that looks like it's a little bit closer to 7. So I would expect that the most abundant isotope is going to be lithium-7. So I'm going to write lithium-7 is more abundant, which just means it's more frequently found in nature. And the reason for that, so we are going to explain also, because the weighted average atomic mass is closer to 7 than 6. Yeah. So every now and then I like to throw out like not so mathy of a calculation problem just to make sure that we really understand what we are doing here when we do this math, right? Okay. I actually want to flip to the back page. So for honors and on levels, y'all's assignments are slightly different. I'm going to go to the chart for calculating uranium. So honors, this is question number 6 for you guys. On level kids, if y'all are watching, this is question number 4. So y'all are still on the front page. The question is exactly the same, but I thought that this would be a great opportunity for us to practice another one of those calculations like we just went through for magnesium on our notes assignment. Okay, so let's see. It says calculate the average atomic mass of uranium according to the isotope data below. So here I've given you the isotopes. There are 3 of them: uranium-234, 235, 238, right? And the more specific or more exact mass. Once again, there's slight variations, very minuscule, especially when I'm considering an AMU as a very, very teensy-tiny thing. That is nothing for me to be too concerned about. Me saying that that is basically 238. But we got to keep that exact mass into our calculation going into calculating the average atomic mass. So the first thing I notice here is they're always going to give you the percent relative abundances. Wow, looks like uranium-238 is way more abundant than the other two, but I still got to do the math anyway. I always like to, while I have my percentages here, I like to move the decimal 2 places and turn them into that decimal form. Now, do not get freaked out on these sneaky small numbers. I know you're like, oh, cool. It already looks like it's like in decimal form because it's like a decimal and then like it's at the very, no, you still have got to move your decimal 2 places to the left every single time. So what this is going to be is this is going to be a 0.00, right? And then 0.1, right? And then this guy right here is I have 2 places that way is going to put me at a 0.0071. And then finally, this guy right here, I move my decimal place 2 places, or excuse me, yeah, 2 places. And then I go 0.9928. So these decimal values are what I'm going to be multiplying each one of my masses by. Okay, are you ready? Here we go. We're going to do our work for each isotope. It's going to be a little bit not sloppy. It's going to take up a little bit space, but that is super fine. So I have 234.043. And once again, these are measured AMU. That is a unit that needs to go with that number, right? And I multiply by his teensy tiny percent, 0.0001. That does not need a unit because that is just a percentage, right? This is not a grams. This is not a liters, okay? And then I have plus my next isotope is 235.102. That is a thing that requires a unit, AMU, times his percent abundance, 0.0071. And then plus, I got 238.055 AMU times 0.9928. I'm almost ready to get a room. That's okay. Yes? So these are all of my isotopes. I'm going to grab my calculator and get ready to type everything in. So I got 234.043 times 0.0001 plus 235.002 times 0.0071 plus 238.055 times 0.9928. Okay. All right. So my calculator gives me this. I'm like, cool, that looks great. So I'm going to write down my answer, or my average atomic mass of uranium is 238. Average atomic mass is to the 100th place on my periodic table. So I have, 0, 3, and the units are AMU. So this is the work for showing average atomic mass. Is not a lot, which is good. And oh, I can check my answer because uranium is a real element. So let's see if his average atomic mass is somewhat close, if not exactly the 238.03 that I see. So your uranium is down here on the bottom. Wow, that makes me feel real nice and cozy inside. Once again, your periodic table is here for you guys to check your work, right? But you cannot just be like, oh, well, the answer is, let me grab my periodic table. I want to see that math work shown. So that's our lesson on average atomic mass, and I hope that you guys had a lot of fun with that, and I will see you tomorrow.